Our goal here is going to be the same as it is with a system of Cartesian equations. That is, to find the coordinates of the point, the x and y values, where the two equations are the same. And using t as the parameter for both sets of equations here is a little misleading. We don't really care about the parameter, only the x and y values. It's possible, even likely, that the parameter values that give us matching x and y coordinates will be different. So to see what's happening, let's look at the graphs of the equations. First, you can confirm that the solution to the system of equations is 1, 4. Now, keep an eye on that point as we go along. We'll actually talk about how to find the intersection in the rest of the lecture. When t equals 0, the first path is at 0, 2, and the second is at 4, 1. Now, when t equals 1, the objects moving along the path have made it to 1, 4 and 3, 2. Notice how the first object just made it to the intersection point, but the second one isn't even close yet. Now, when t equals 2, the paths are at 2, 6 and 2, 3. And when t equals 3, they make it to 3, 8 and 1, 4. The second object or path has finally made it to the intersection point 2 time units after the first one did. So there are really two different questions we can ask here. First, where do the paths intersect? And second, do objects moving along the paths collide? That is, do they both reach the intersection point at the same time? Now, for our system of equations, the answer to the first question is 1, 4, but the answer to the second question is no, because as we saw, 2 points moving along the paths get to that point at different times. So to help clarify this, when we're looking for the point where paths cross, I'll emphasize the fact that the parameters aren't linked by using two different variables. Usually that's going to be t and s. So what we're looking for here are values of t and s that make both the two coordinates, the two x coordinates the same, and the two y coordinates the same. And if we substitute the expressions for each of those coordinates into those equations, we get a system of linear equations you can solve using your favorite method, either substitution or elimination. If I set the x coordinates equal, I get t plus 1 equals 2s plus 3. And if I set the y coordinates equal, I get 2t equals negative s minus 1. Now, if solving this system of equations, you can do this, like I said, using your favorite method, either substitution or elimination. Doing that is going to give us s equals negative 1 and t equals 0. Now, this isn't the final solution. Right? We're looking for the x and y coordinates, not the values of the parameters. So if we use t equals 0 to calculate those values, we get x equals 1 and y equals 0, which makes the intersection 1, 0. And you can check this by substituting s equals negative 1 into the second set of equations, and you'll get this same point. Now, thinking about our second type of question, 2 points moving along these two curves would not collide since they get to the intersection at different time values. That is, for different values of their two parameters. We can apply the same procedure here, setting each coordinate formula equal to the corresponding formula from the other set of equations. But doing that is going to give us a system of nonlinear equations. And these can be a little more challenging to solve. They can require a little more creativity. So I'm going to go through the solution to this one in a little more detail. Now, the first thing I'll do is take each set of equations and put it into the standard form where the variables are on one side and the constant term is on the other. And when I do that, you're going to notice both equations have this 1 over s squared term. Right, so if I add the two equations together, those terms are going to cancel and leave me with something that just has a t. So solving this for t gives me t squared is 8/10 or 4/5. So t is square root of both sides here, plus or minus 2 over the square root of 5. Now we need to stay focused on the question. Right? Force of habit might make you want to substitute back into one of the two equations to find the corresponding value of s, but we don't need that. Remember that we're trying to find x and y coordinates, and we can do that by calculating x1 and y1 using s equals 2 times the square root of 5 and over here on the y side, we're going to get 3 over that square root expression. And there's our 2 points, right? Excuse me, there's our first point. 25/4, comma, negative 13/4, right? And you can confirm it if you put negative 2 over the square root of 5 back into those equations, you get the same answers as well, right? So the intersection really is just a single point. Now, at this point, some of you might object that I didn't simplify the value of s, right, by rationalizing the denominator. And you'd be right. If that had been the final answer, yeah, I would have gone ahead and done that. However, since it was only an intermediate value and rationalizing wouldn't have made it easier to work with and would arguably have actually made it harder, I went ahead and left it like it is. Before we jump in and start playing with the equations, stop for a minute and think about what we're looking at. The first set of equations represents a circle, whose center is at the origin, and the second set represents a line that passes through the origin. The thing about the geometry gives us a head start, since with that geometry we know to expect 2 solutions. Okay, now let's work through our procedure and set the 2 x-coordinate expressions equal to each other and the 2 y-coordinate expressions equal to each other. Now, if we add those 2 equations together, the s parameter, the s variable, is going to cancel, and we're going to be left with cosine of t minus sine of t equals 0. Right? And if we add, let's add sine of t to both sides, we get cosine of t equals sine of t. And we know, right, that the only place where the cosine and sine are equal to each other is when t equals pi over 4 or 5 pi over 4. All right, and that's what we need, right? If we substitute those t values into the first 2 equations, we are going to have to do it twice this time. x1 of pi over 4 is cosine of pi over 4, which is the square root of 2 over 2. And y1 is minus sine of pi over 4, which is minus square root of 2 over 2. So there's our first intersection point, the square root of 2 over 2, comma, negative square root of 2 over 2. And then I'll do this again, right, to get our second point. x1 of 5 pi over 4 is cosine 5 pi over 4, which is negative square root of 2 over 2. And y1 of 5 pi over 4 is negative sine 5 pi over 4, which is plus square root of 2 over 2. So there's our second intersection, negative square root of 2 over 2, comma, square root of 2 over 2. All right, so now that we've seen examples of parametric equations and have some experience with how to work with them, we're ready to start actually adding calculus techniques into our toolbox.